Okay, this is a central unit for and is definitely the most important for physics. What we're going to talk about is resonance, and as I point out in the first chapter of that handout that you've just gotten, without the phenomenon of resonance, we're blind, deaf, dumb. Everything that we communicate with humanly is impossible without the amplification that occurs from resonance. So today we're going to really quantify that with the first kind of resonance, and that's linear resonance. The other kind of resonance, parametric amplification, is a much wilder kind, and I alluded to that as being very powerful, and in fact underlying the snap action that the trebuchet gave. But today we're talking about something much gentler, but in a sense much more important. And the idea also is that without resonance, nothing happens in quantum mechanics at all. So underlying all of our classical mechanics is the phenomena that we're going to introduce very carefully today. So one of the things I want to get across very quickly is the basic idea of making a figure of merit for resonance in a way that you can understand. And what I call the 5% solution, we'll see that early on here, and then it appears again and again as we go into the discussion of amplification factors, quality factors. Another word for this is finesse. We'll hear that when we do more wave action in the next lectures. But what I'm most interested in is giving you a familiarity with the Lorentz Green's function here. This is a good way to introduce the mathematics of a Green's function. You've had probably a little bit of that in electromagnetism. This is the much simpler one, but it shows how Green's functions work. They're funny kinds of inverses of differential equation operators, one way to describe them. Now, we are jumping here to lecture 20. I don't know if you heard me when I said that the lecture 19, which is on constraints, is a self-study one. But all of the stuff that goes with it, in fact, we have the class lecture for that left over from last time. That will show up on the website. This is the hero, I think, of the resonance world. And what he did was measuring the speed of light about 1,000 times more precise, and then realizing after he'd done that we needed to change our metrology. He hectored the entire world to declare the speed of light as a definition of the meter. And that made it much more easy for people that wanted to do high precision work, such as people that were thinking about making a global positioning system. It wouldn't have happened without this gentleman's efforts. And if he hadn't have died from ALS, he would have shared the Nobel Prize in 2005, which was John Hall and John Hall worked sort of across the street from Ken and shared authorship of many of the papers that he wrote. So here's the basic equations that we deal with if we're just doing a model of resonance and trying to see how all of the effects, and that includes, and this is pretty much the first time in our class here that we actually consider loss, friction, the coefficient of a first an odd derivative, derivative of order 1. So since this is absolutely mandatory to do this because it's the thing that affects how precise the resonance is. So we're going to take this apart. let's just jump ahead here to where we have just the oscillator by itself. And we'll make sure that the notation that we're using and some animations that go with this are in effect. Of course, here is where we'll use the phasor, and we'll have the real axis sitting horizontally and the imaginary axis setting vertically. When we get to talk about waves, we're going to rotate that by 90 degrees. But right now, we'll have the real axis be where it usually is for people that do engineering. The imaginary part basically is the velocity divided by the frequency, so that we get a circle instead of an ellipse for the phase space orbit. And what else do I need to say? This effect right here is totally due to the restoring force that we're assuming is linear. And for small oscillations of anything, that's what you deal with. And we are talking about actually amplitudes that are quite tiny for most molecules and atoms. And so this is very effective, very good model. And it's occurring here with our usual kz, but the k is this omega 0 squared, and the frequency, angular frequency, is what we're dealing with. So the force, this thing right here divided by m, that is the frequency squared. So k over m is omega 0 squared. Anything else? I think this is all very familiar. But I also want to, while I'm doing this, make sure that the animations which follow can refer back to this very simple case where we study in detail as time goes on a 1 Hertz oscillator. Okay, well, it won't be quite 1 Hertz when we animate it. I'm going to make it 1 radian per second in this room. This will be the real time for this thing. So I'm going here, making the oscillation. Let's start counting right here. 0 chimpanzee, 1 chimpanzee, 2 chimpanzee, 3 chimpanzee, 4 chimpanzee, 6.28 chimpanzees. So this is taking this thing two pi seconds to actually happen a cycle, actually do a cycle. In any case, this is available to you, like all of our stuff, all of the stuff that we do on the web. And at any time here, you can change the scale just by doing the mouse wheel and expanding it, and or contracting it. And we're going to be running most of them around 15. Reset time equals 0 to get this going again. And what we're going to study is how long it takes for various things to happen when you turn on a little bit of friction. So the oscillation here would go, as if this graph was big enough, all the way down to Fort Smith. That's how long we're going to be running some of the things we're doing today. But the basic idea is to figure out, in terms of the units, the angular frequency and the real frequency, which differs by 2 pi, for all of the effects that happen. We turn on the rest of this equation of motion here. So the next thing, as I say, is friction. So we're going to turn on the friction. We're going to leave the force at 0. This is just an autonomous oscillator, but it's got some friction now, and we have to figure out ways to catalog that, to measure that, to state the presence of that friction. So here is the equation as it stands for our calculation. We'll do the calculation that you've seen probably in sophomore physics, but we're going to be a little bit more careful with it. So the basic idea is that you apply the trick of a homogeneous differential equation. It's nothing but linear combinations of derivatives. That's the case. The good old exponential, complex exponential, with a minus sign. The minus sign means that we're doing left-handed rotations, as in a clock. It has to be going this way when it has a positive velocity. That is positive. And that leaves us with just a left-handed rotation, a minus sign here. That's throughout of quantum mechanics, Schrodinger type quantum mechanics, you see that minus sign. So keep it right here for a couple of reasons. In any case, by differentiating that thing once, getting a minus I omega, and twice, getting two of them, gives you a quadratic equation for the frequency. The complex frequency is what we're really getting here, the solution to this quadratic equation for that omega. And that, from high school, is simply a combination of something that is imaginary and then something that's real. Okay, so it's complex number. We're talking about complex frequency here as a way to treat these resonance. Okay, now I'm going to go ahead and pause this thing, get the other screen back again, get it up to speed here, and this is where we actually put the solution to this into the exponential. And if you do that, you get two factors seen at the bottom there. So I'll go real quick to that, and I'll make this one have that same thing. So here's where we interpret the solution that we're getting for this, the damped harmonic oscillator. And then I'll put an actual damped harmonic oscillator in the center screen here in just a minute. But the thing that I want you to notice is that while the damping will have an effect of quite quickly reducing the amplitude, that's this factor right here, it will fall exponentially. But for very small gamma, that could be quite a while. Talking about radioactive decay, 6,000 years or something like that. We're talking about stuff that we're doing, seeing light in this room. Well, it's more like picoseconds. Okay, so this time that this thing lives is very wide in physics. And at the same time, it's going to reduce the frequency of the oscillator, but not by much. And that's the thing that I want to make clear right at the very beginning here, is that the effect of the damping here reduced very slightly. In this case, with a damping of 1/5, it's being reduced by 0.05%. That isn't much. We're talking about 6.2. This is 2 pi right here, minus something that's in the third place past the decimal. So we've got this. This is something that you won't notice in the graphic that we're going to do. Probably doesn't hurt to go ahead and start that graphic right now. This is the simulation for that. And the thing that we're looking for is how long does it take to kill the amplitude so that it's only 5% left. And the trick to that is to notice that e to the minus 3 is 5%, very close to 5%. So the amount of time it will take to do this will be 3 over gamma. And it probably doesn't hurt to go ahead on this slider here and show that. This is what I call the 5% solution to get this figure of merit for an oscillator. How long does it live? Okay, so it's easy to recall e to the minus 3 is two figures, 5%, 0.05. So that means that the time is just this 3 divided by whatever gamma we've picked. We've picked 0.2 for all of the simulations, pretty much all the simulations we'll do. On the first part of this lecture, 3 over a fifth, that's 3 times 5, is 15 seconds. That's about the length of the graph that we were making just a few minutes ago. And that is when you'll see this thing decay up to 5%. Now this is the old graphics that we used to use all the time. Here's the brand new stuff going to work here. And the exponential curve that is relevant to the amplitude is shown there fairly clearly. And what's interesting about this envelope is that it touches the oscillation curve here. And
close out some of those windows, if you would, Professor Harter.
Yeah, maybe we could go ahead and kill some of those things. That's probably what's killing this thing. Get rid of that guy, and I'm just going to go Command W all the way down the line here.
Yeah, relax. Yeah, I had a lot in there.
And come back to the lecture and get started again. Sorry. Get it started.
Struggle starting up.
Okay. All right. In any case, the envelope is tangent to this curve. That means it touches it just a little bit past the peak. It's hard to see that. In any case, that's two units of time, okay? But that's 2 times 2 pi actual time in this room that we're talking about. And what this is predicting is at 15, and you can see where the curve for the envelope is, this thing is going to be down to 5%. And you think about, if you're thinking about money in a stock market that seems to be decaying these days, when you get to 5% of what you had, you consider that you're pretty much a total loss. Okay, so that's the other reason to use 5%. Now, what I point out in this, and we're almost there, we've got a couple more units of time to make it to 15. But what you're doing here is almost, but not quite, a perfect logarithmic spiral. We'll see later on when you make it go faster, like that it is not a logarithmic spiral quite. So the whole bunch of things that are happening here that aren't quite what you would say, it's not quite at the peak envelope and so forth. There we are, we're just about there. That's the 5% point right there, just passed on through the 0 at that point. Now, if you're going to be precise about imprecision, it doesn't hurt to go on this one to a more precise one. Now, this is just something I thought up after I got done with. How can I do better than that? How can I make some bad thing that's happy? E to the minus pi, you don't see that very often, but you should. In quantum mechanics, that's talking about a wave going into an evanescent region. This is a good way to see how long half a wavelength you would make a 4%. It's 4% instead of 5%. But it's easy to remember. It's 0.04321, which is kind of cool. All right, so e to the minus pi is a number you can remember almost as easily as the 5% that gives you e to the minus 3. Right, that's what we're dealing with here. So it would be pi over gamma. That's pi over our 0.2 that we've chosen. So 15.7 isn't much different from 15 as far as this business goes, but if you really want to be precise, that's what you would play with. And we'll bring that up again later on when we make an approximation into an exact description of uncertainty, which is where this is leading. Okay, anything else? Writing this thing out in terms of the functions, the omega gamma, that's the real part of the thing that we obtained algebraically. When we say that the number of heartbeats, the number of times this thing has to wiggle is 15, if we're doing it approximately, but it's 15.7 if we're taking the exact timing there. All right, so let's go ahead and this one as well. So there's the basic formula for numbers. Now, it's time to put a stimulus onto this system. And this is where we get to discuss the full Green's function that we're going to be getting for the solution to this. So here's this guy we've taken care of. This was the first thing we did. Got to do that. Okay, so we're imagining an acceleration due to an electric field. That would be a typical thing if we're just talking about light coming in and doing something to chromophores in your eye, or a laser making a molecule dance a little bit so it shows its spectral. And so we would probably be writing a force here, and it would be the acceleration, that's the electric charge times the electric field, but then divided by the mass. So the E over M ratio that we talked about last time with respect to magnetic oscillations, here it shows up again. And the force due to that stimulus is just this without the mass. Okay, so what we end up with here, if we're going to go ahead and divide the mass out of here, this gamma here, the coefficient of the velocity, say the letter B for that, we won't use that again here. We're going to be writing 2 gamma m. Now the 2 gamma there is just to make the algebra one character less complicated. So, and it's also a good notation that you will see in other places. So that's a key thing to remember. And let me get this guy back to the original lecture and advance it so that we can use the best graphics on the brightest screen here. So here's what we would do in order to solve for the solution Z, the complex solution, to the full damped forced harmonic oscillator. Okay, so harmonic, damped, and now forced or stimulated harmonic oscillator. So what we have to do is get 1 over this operator, right? That's called a Green's function. Okay, except that this operator has 0 eigenvalues, so this is not defined as an inverse. We have to get them out of the way in order to make a Green's function. But that's not something that really bothers us here, because if you are willing to assume that this crazy thing can be done, it's not crazy if your stimulus is a Fourier component, and in particular if it's just one Fourier component with a stimulus omega s, s for stimulus, okay? So we're going to imagine that that's what the stimulus is, right? Absolutely pure tone is going to be working on this thing. And then it's not very difficult to go ahead and take those derivatives in the denominator. And that's your Green's function right there. So the double derivative that was there gave me that. The single derivative gave me a complex thing with a 2 gamma in front of it and gamma minus I, and then stimulus frequency. This is stimulus frequency squared from the double derivative. And then omega squared's in there all along. So we rewrite it with different order. That's what we call the Lorentz Green's function. Got to bring another guy into this eventually, but I want to point that out later. So I use the green letter G for a very famous fellow. Okay, now he looks like he's out of one of those gangster movies or something. This is George Green, and I'm especially putting him up here. He's born in 1793. You can find in the British church a tombstone that marks him. So he's very well known to British science of that era. In any case, we need to get familiar with this function. its geometry, all sorts of its physics, its peculiarities, and benchmark it and do all that stuff. So let's go ahead and get that started. So basically what we're going to imagine is a sort of a block diagram where a stimulus comes along, hits the Lorentz Green's function. Put Lorentz in there too. Here he is. Don't want to leave him out. He's got the same birthday I do, so maybe there's some connection here. Okay, but he looks a little bit more civilized. And now you're talking 1853 to he dies in 1928. Long lived, lots of things he did. Lorentz Transformation. He figured out algebraically anyway, way ahead of Einstein, how you could think about light, but then he didn't put the think into it. It didn't say, he just thought, this is queer, that probably doesn't happen, and missed out inventing relativity. The thought experiment wasn't done completely. So what we have to do is take this inverse complex number and get the real and imaginary parts of the actual G function. And that's easy to do with this simple. If you're going to take that inverse of a complex number, you have to multiply and divide by the conjugate of the number in questions, because that leaves you with a real denominator, and then the complex thing, actually the conjugate thing, shows up in the numerator. So that's what we're doing here. We're producing first the rectangular form for this function, and we will plot that profusely and often in just a bit. But then here's the polar form. We're also interested in the polar form, and this angle is really key to what happens in resonance. It is the indicator of whether energy is going in or coming out during a resonant transfer. And that is what I want to make sure we clearly understand. Bring all the screens up to snuff here to talk about that. And the idea is that the phasor for the response will have a lag, usually, to start with anyway, and the way we're going to describe it here, a lag angle rho. And that is this angle right here. It's just the arc tangent, inverse tangent, of the middle frictional factor divided by the difference of the squares of the natural frequency with the stimulating frequency. Okay? So that's what we're going to be looking for. We're going to be looking for that angle when we do phasor diagrams of a resonant process. And that particular angle will be right at the center of a triangle that consists of the real part, that's the real part of the Green's function right there, and then the imaginary part right there. But that whole thing is going to be rotating at the stimulus frequency right here, omega s, that we set. We're going to be measuring, we can tune the laser. And the molecule's got its natural frequency without, we usually can't change that, but we sure can change our laser frequency very nicely using dielasers and all that kind of stuff that are part of this building. So this, I really point out that row to make sure we know what we're talking about. Now here's a picture of what we're going to be plotting, and I will go ahead and do the plot in the center screen here, but we should be getting something that looks like this. And I will get it by simply going here, and I should be able to get it right away by clicking that. There we go. Now one of the things you can do with this graph, it has a very nice feature that lets you, by simply right-clicking, well, I guess that gets me in a screen, but I'm sorry, rolling the mouse, that is, if you have a button there and you roll it, you can change the a vertical scale as well as a horizontal. I kind of like the way the horizontal is right now, so I won't touch that. but this is giving you a chance to see what the real versus imaginary parts of the Green's function is. And it looks like a perfect circle, but it's not quite perfect. It's got a little flat tire that you can see if you really expand this thing. And that flat tire corresponds to what the most important part of the start of a resonance. And let me just go ahead and jack the scale up here. The important part of looking at the response of something is to ask, how does it respond at zero frequency or low frequency? That's this distance right here. And that's the flat tire. The flat, this thing right here, is exactly that length. And so what we're interested for a figure of merit is the ratio of what's called the DC response, direct current response, literally. And I'll go ahead and bring this thing up to speed here as well. But there's sort of an anatomy of what we're talking about right there. And we're interested in the response at resonance, which is just about, but not quite exactly, at that point. This resonance is occurring here at 6.28 in the radian scale, radians per second. Okay. So right here is 1 hertz per second. Our frequency in this imaginary resonance situation, and this real part, the real part of the Green's function is stuck to the magnitude function, turns the corner right there, comes back down to here, and then goes back there. That's the real part. Imaginary part, just essentially zero, very close to zero, in fact, exactly zero there, and then peaks out right underneath the thing. Let me drop the scale back down here so you can see that. You can see the other thing that I want to point out about this right now, and we'll talk about it later, is this is halfway. Not exactly halfway to the peak, but very close to halfway, within a pixel or so of halfway. And so is this one, but a little bit less than halfway for one that would be turned over. So it's that geometry that we need to get familiar with. Okay, let's see if there's anything else I need to say. Let me bring the next slide here before we go on here. We're plotting imaginary part in a sort of a green. Okay, the outside response here, the part that you see on this graph, sort of a orange-yellow, and then the imaginary part is that light green, and then the blue part, this real part, okay, sort of a cyan in both of these plots. Okay? Now, as I said, this ratio is what somebody that's going to use resonance to get something going is really going to be interested in. How much of a gain do I get for the resonance response? Well, this function right here, when I set omega s equal to omega 0 and get rid of that, okay, the real part with omega 0, omega s, 0, okay? This thing is going up following the resonance, and it says, uh-oh, I'm going too high, and about halfway. This is why we call this a full wave half maximum, because it is very close, but not exactly at the halfway point to resonance. It just goes bang, boom, down to here, and then boom, back up again. And, you know, for tiny resonances, this region is really tiny for high-quality resonances compared to what you would normally consider the range of action for this. So this one right here, when omega s equal omega 0, and it's the magnitude I'm talking about here, so it's the sum of these two squares square rooted, that is not 0. That just keeps going right up to there, and then turns around and comes back down, and then dies off. roughly with this right here. This imaginary part is only appreciable within the resonance region of full. This is a full wave, half maximum. It's half the maximum, and I'm taking both sides. That's the full wave. HWHM is half wave, half maximum. That's also a number that's of interest very often too. It's just half of what we're talking about here. So that turns out to be omega 0 over 2 gamma. Seen that number before? Okay. That's what I call angular quality factor. Little q. Now you'll read most books, you're going to learn it as an energy effect, and then it's big Q. We'll get to that in a minute. This is the one that is worth looking at. And it's, as we'll see, exactly the number of heartbeats that this oscillator has when it's punched and left alone to fall to 5%. The 5% solution is that there. Okay, now let me see if there's anything that I missed or made a mistake with. Don't forget the lag angle here, and that is very close to 45 degrees when you get to the end points of this almost circle. This is really close to being a circle, and we'll see why that is. When we talk about the Lorentzian, the Lorentzian, the quantum Lorentzian, that is not squares in the denominator, but just linear thing. We'll see that we can approximate this thing with the, is the quantum Lorentzian. You lose the DC response, and you get a symmetric function. Okay, anything else here? Resonant response versus this, okay? So what we're talking about here is a resonance response that is 15 times the DC response. 15 was the number of wiggles we had, a number of heartbeats we had to get to 5% decay. That is also this very important factor, omega 0 over 2 gamma. Okay? So there's just a few key numbers here that we have to remember, and everything else kind of falls in place from those. Now, I think we could probably go on here just pointing out that if you go from gamma equal 0.2, which is what we started with here, and made it, and here's a blow up of both of these plots. But as soon as I go to 0.1, I double how high that thing goes. It's way up there, right? And the halfway point is about where the top of this one is. Very close to that. And this is now the halfway point for this resonance, okay? So this is a skyscraper in New York. This is one in Dubai, okay, where they're building things that they're going to try to make a 1 mile high skyscraper, all right? We're working on it, all right? But right now they already got one that's up there around 2,000, I think. Okay. So that's a pretty high gamma. Now, the thing I want to emphasize, and this means that you have to go twice as many heartbeats to get rid of 95% of your amplitude if you've got gamma equal to 0.1 instead of 0.2. Right? The thing I want to emphasize is how enormous this omega 0 over 3 gamma, or 2 gamma, I'm sorry, is when you're talking about, say, your eye, or any atomic transition that gives light. How many heartbeats does it take for that to happen? And that's, as I'm going to show you, also what this quality factor, omega 0 over 2 gamma, means. And typically for an atom, you're talking of 100,000 to a million. I mean, it's just incredible how many wiggles it takes to get light in and out of a molecule or an atom. Molecule, even worse, it's in the millions. And this has happened every time your eye sees, I look at a shirt and red comes to my brain, okay? Got 3 of them here, right? So it happens 3 times as fast, okay? But still, you're talking about the chemistry is actually going on in microseconds. Just incredibly fast, right? That's resonance. Real resonance. Okay. All right. Now we've got one other detail to do here. Here's our response. Okay. As Green and Lorentz would give it to us. And this is known as the inhomogeneous solution to the differential equation that we're solving. But there is also, and you can add this, any amount of this to the solution that we've been talking about when we plotted this. Any amounts of this, because the effect of this being acted on by differential equation is exactly 0. This is the null space of the differential operator that we're talking about here. What we need this for is to set the initial conditions, or the boundary value, if you're talking about doing Green's functions in electromagnetism. Okay? You get this thing fairly easily, and then you've got to find this in order to set the initial conditions. And we've been setting the initial conditions to 0. We assume a cold oscillator when we apply the stimulus. And if we do that, then this thing has got to be the magnitude of this thing at time equals 0 with a minus sign. So this cancels that in order to give me 0 here at time equals 0. So there's the whole solution that you need in order to satisfy initial values or boundary conditions, boundary being time equals 0. Okay, so that idea right there is important throughout physics where you're solving wave equations of any kind. So there are other names for this solution versus this solution. This one eventually dies because of the exponential. It's got a certain number of heartbeats. It's given by 15 in our case. After 15, this thing is down to 5%. You can hardly see it, especially if you square it. And this thing has just been going ever since you started. It hasn't changed at all. It's just oscillating at the stimulus frequency with a phase lag of some kind. Or phase lead. That may be negative, may be positive. So, in any case, this is not a steady state because it's been there as long as the stimulus is turned on. But this one's going to die off. So it's called the transient. So the transient part of the solution is this one. Okay. These are all terminology that you have to get used to knowing or reading literature. And we're not just talking about classical oscillation. The very same stuff is used for the quantum mechanics. It's just a little cleaner than this. This is a Lorentz Green's function. The Lorentz function is much simpler, as we'll see fairly shortly here. In any case, this is a picture of a typical resonance situation. And to get that, I'm going to back out of here and go forward to that part of the lecture that has that. Okay. So let's go ahead and just see what it looks like if I'm way below resonance. And I should be able to just click on this and get that to come up. There we go. Okay, so we're talking about a force phasor here now that has just woke up the poor oscillator. It was sleeping happily here, and this got turned on. Okay, so it's trying to catch up with that force. As you can see, it's catching up and growing. Oop, it just passed it. And as soon as it passes it, the phase is in such a situation that it takes energy out of the oscillator and into the force. And then it gets behind there. Now the force gives energy back to the oscillator. This is starting a second beat here. This is one beat, and then there's another beat. These are the beats of the transient. And we'll only get a couple of them, or maybe three, before we hit the 15-second deadline for the transient, the 5% deadline for the transient. Okay? And you can see the transient is there sort of hugging the thing. It's a little bit behind now, and so it will grow a little bit after that. You can see that the amplitude is gaining. It was falling, and now it's sort of rising a little bit. We're only at 12 now. It's still behind there, so it's going to maybe rise it just a little bit more, but we're kind of getting at the point where the exponential has killed it. It's not going to do much more, but just hug onto this thing with a phase lag of 0.14 radians. That's what we're talking about here. That's not very much, but you can see it on this graph. Okay? So this is a typical situation where we're getting more than the DC response, but not much more. Okay? We're on the resonance curve out there just a little bit higher than the DC response. And the phase lag is hardly detectable on that graph. We have to look on this graph and see, and then that's the actual number for the phase lag. So this is typical below resonance behavior. We have some beats, and the further I get below that, the more of the beats I get, but the beats will be very small as I approach the DC side of this thing on the resonance curve. And that's the Lorentz green curve that I'm talking about. Okay. I guess it's worthwhile just going ahead and jumping to the next situation here, which is this. So I'm going to make this stop so that it doesn't eat up CPU time and spoil what we're going to see next here. On resonance, and this is still with our 0.2 15-second timing. Let's see if it seems like it's getting
interesting.
Yeah.
Luckily it hasn't hosed us.
Okay. That's not very nice that it does that. We have to kill some more of these things up here.
Last time.
I guess I do. I'll just get us back here so that they don't interfere at all. And then I'll just start it over.
Well, abhor it. Abhor it's a hog.
You think Borit's the villain here?
Probably not, but this is the
Okay,
first time I've
This
seen
is working well enough. We don't have to do anything more. But anyway, what's interesting about this is that when I get on resonance, then the real part of this function, and you really have to see that by going back on this slide right here. I'm going to go back, get the function out. You have it over down there. But here's the real part. When you have exactly the stimulus and the natural frequency matched, this is zero. That's where the real part is. Turn the corner and going right through here. Okay? So with the real part zero, you have a phase lag. That's the angle, the arc tangent of this over zero, that is the arc tangent of infinity, is 90 degrees.
Mm-hmm.
And you can see that 90 degree thing. This is a perfect right angle, very nearly perfect right angle. Okay, that's the best you can do in resonance. If you want to get 90 degrees out of phase, just think about it as this force here attached to the stimulus. It's adding to it as much as it can. It's adding in the direction of the velocity. The force and the velocity are matched. They're in phase. The force and the position are 90 degrees out. This is leading by 90 degrees, so it is feeding this one. Not much now because the friction at this point is killing everything that this force puts in. It's reached, and we've gone past 15, it's reached the steady state, very close to the steady state. It was probably indistinguishable from the steady state on this graph when we passed 15, okay? When we passed that, that magic number, the 5% lifetime, which is also our quality factor. So we're talking about a quality factor of 15 here. Not 15 million, which is more like, you know, resonances that involve the light we see with. More like maybe 1500, which is the cue of little cilia in the cochlea of your ear so that you can hear. You need a pretty healthy resonant factor there to not be half deaf like I am. I'm wearing hearing aids to get the high frequency going again. You have gamma equal to infinity on that region of the spectrum, acoustical spectrum. Okay, so this is just going to be a flat curve. You can see it's not getting any bigger. That's the limit of this particular resonance. Okay, now let's see if there's anything else I need to say here. I'm going to go ahead and pause this. What it's worth seeing, and this is something I would encourage you to play around with, so we have these things available on the web. You can open up a control panel and change all sorts of things, but you can pick a particular frequency, a particular gamma, all of that kind of stuff. You can also get it to show the steady state response, the transient, and the total response. Okay, and obviously the steady state response, eventually that arrow becomes Z as the transient part dies. So that's worth looking at. Now, in this particular case, the damping is essentially turned off. Not exactly turned off because that would cause the computer to have some infinities that we don't want. But the idea is that here, every cycle puts in the same amount of increase in amplitude. This is linear resonance, a straight line that we saw when it did this. The resonance, you know, started out fairly straight and then had to settle down at a constant amplitude. This never settles down. This is more like the resonances in your eye. It takes hundreds of thousands of oscillations before it reaches its steady state, and then by then your brain can read the impulses that come up the nerves to tell you red shirt or whatever, right? So these particular examples here, these beating simulations, are worth playing with, just for the, you know, just to get a feeling for the things that can happen during the resonant process. I want to do some more making sure that we put all the quality factors together. We've got the little q defined here as the natural frequency, and that's the natural frequency totally independent of the friction coefficient. Omega 0 is what the spring would give if there was no friction at all. We're dividing that by the friction coefficient, twice it. and actually the friction coefficient is 2 gamma, so it's the omega 0 third coefficient divided by the second coefficient of 2 gamma in the differential equation that we looked at first. So this amplification factor is also, I mean, it is the number of oscillation it takes to get to 5%, but it is the amplification factor that we're talking about here. So whatever I pick for a force here on this scale, that is going to be whatever I pick for the amplitude of the acceleration, that is multiplied by 15 at the, you know, when this thing reaches its limit. Okay. All right. I'm going to go ahead on both of these screens here. This one I've already said, but it's also important to get that straight. Let's go ahead on this screen here for a couple of numbers. This one right here, called the heartbeat count, measure of the lifetime. Okay, that was what we talked about first. It's the 5% time times the frequency. Frequency is essentially that. It's actually omega gamma, but do you remember those frequencies only differ in the third decimal place. So the product of number of oscillations before you're bankrupt, 5% down to by 95%, the heartbeat count. And that's something you ought to think about. How many heartbeats do you get in your life? It's not, assuming you don't do something stupid or get some nasty disease, okay? It's on the order of 2 billion. If you have a really slow heartbeat like I do, with 27 or something like that, maybe I get to go longer, maybe not. But that's, you know, a measurement of a typical infrared resonance in a molecule. It's 2 billion. Every time the infrared transition occurs, it's got to do 2 billion to get the energy out or in. I mean, that's it's hard to imagine that, you see. But we have graphics here where we show 15 for that factor, right? And it's pretty good resonance. I mean, it's about what I would get if I took a feather and moved this heavy weight. And what I have to do is I have to get in sync with it, right? And that's what the pi over 2 is, you see. I'm only doing half of it, I should be coming on the other side, but that's good enough to get it going, just with a feather. So that's an amplified, I'd say that thing has probably a phase factor, not 15. You can see it's going to last a long time. I would say it had, I've counted it, and I'd say it's well over 100 for this heartbeat count and the amplification. Okay. So those are the numbers. But here's the number you read in most of the text. Okay. They look at the energy, which is the square of the amplitude. Okay. So that's e to the minus 2 gamma. This falls off, you know, twice the rate. Okay. And gives you a dE is minus 2 gamma E. Okay. That's the standard quality factor. It differs from us, but just by a 1 over 2 pi factor. Okay, so it's really not in this one I like better. That's the one that you'll see in the literature, engineering literature and physics literature both. Okay, it's the relative amount of energy lost per a cycle period. Relative being the ratio of the change to the original. That's 2 gamma over nu 0, not omega 0. So that's 2 pi over little q is 1 over the quality factor. And remember, the basic idea is, and I make this point in the preface to this unit, the quality of the oscillators that a society produces is pretty much in direct proportion to the quality of life of that civilization. And we're getting some real high quality now because we're getting this thing up to 10 to the 18th at Boulder Labs and at NIST. Okay, we'll talk more about that later in this. We'll be talking about in our group theory class when we do spectroscopy. But anyway, these are, now if you want the more accurate one, fine. That's really precise measure of imprecision, as I say, but we kind of stick with that one. Now, you think of the lifetime of a musical note, okay, if you have something like that. Basic idea is that the change in frequency here, that is the uncertainty in time versus the, what's the beat for the, if you have a guitar and you're making a beat between notes, how accurately can you tune something? So that's the other number that comes out to our little factor here. Okay, now let's go for really high quality that you have in quantum mechanics, and let's assume that we're looking for something that has a really low gamma, something that has a really high quality, and I'm imagining here that as I make so that the stimulus frequency and the natural frequency are, within the ballpark of each other, approaching each other, that I can factor out this omega s. Okay, I'm just basically writing this thing in a funny kind of way. I have to factor that thing, but what I'm going to do here is either take the omega s off of this one, and then just take omega s out of that, but leave it the same here because there's so little difference between them. I could do this. I could have gone the other way, and I would do that if it was somehow the oscillator that I could tune. But here it's a laser that I can tune, so I'm taking the omega s out, the stimulus out. In any case, what I'm doing here is producing what is the real Lorentzian function. This is what you call Lorentzian, complex Lorentzian function that I want you to see. And it could be either omega 0 or omega s. It sits on the outside. When we're talking about molecular atomic oscillators have quality factors that are even over 100, this is as good enough to do the calculations that we need to do. So if that's the case, if I just have a constant times 1 over the detuning minus the decay, these are two numbers that involve inverse time. Okay, so I'm talking about here just the inverse of a complex number, in which I immediately write in this fashion. And we've already done this just for the entire Green's function, but here it is for this this Lorentz Green's function, the kind that we're using in quantum mechanics, where the equation is first order. The Schrodinger oscillator equation is first order. So this then becomes an exact thing. This is what you would want. It's the classical mechanics that harder than the quantum mechanics here. So I'm going to end up with a e to the I rho. That's going to be cosine and sine of the arctangent of the ratio of these quantities. And that's very simply expressed too. This is the ideal Lorentz Green's function, making a perfect circle. Now it doesn't have a flat tire anymore. This, the imaginary part of this was 0 at 0, but the real part had the DC response. That's this distance right here for this particular case. The idea here is there is none of that. This is a perfect circle, and you can see just from the equations here the magnitude of the Lorentz response, okay, which is right there. That sits on a circle that's at this particular phase lag, and as you go up and make the frequency of the del bigger and bigger. Finally you get to the resonance right here. Then you come right back down and go to 0. This started at 0, not at the flat tire point. So this is the kind of picture that you get. And this is called a Smith plot. Where do we see that? Let me come back here to this slide. We'll skip over the animations here and show a picture of that. That's the Smith plot. Now, this goes on a computer screen. That is, you can overlay a screen and plot your, what happens is you change various quantities for various kinds of wavy, I call them wavy Ohm's laws. That's where you have a complex impedance, a complex some kind of current, and a complex some kind of voltage. Okay, so you're solving this equation using this thing. And that's basically what we have here. This is the inverse detuning. The detuning is del. That's how far off frequency you are. You're on frequency when you get on this axis. And then depending on what your gamma is, if your gamma is quite large, you're going to have a small resonance. But if gamma is small, then you're going to be on one of these big circles, you see. And that impedance diagram is just full of intersecting circles, which we've seen before. And I'm going to go ahead on this screen down here to get to that. I'll show all these things. This is a plot that TC just did this morning using analyte to show the dipole function. And that's what we're working with. A bunch of circles intersecting with each other is the dipole function. You can play with that too as the analyte develops. There's another picture of it showing the dipole. Let's look at some of the old pictures that we have. I'm going to go ahead here. That's the geometry of it. You can come back to that. There's a terrible Lorentz function right there. That would be Lorentz function for glue or something. We'll come back to that. But this is what I wanted you to see. Remember this? The 1 over z squared. Okay, that's a field equal to 1 over z squared. All right? There's a 3D picture of it in the old analyte graphics. And here's a cross-section of it, just a little bit off. That's the up and down real part of the resonance response. And there's the up and down Lorentzian imaginary part of what we're talking about right here. So that is the basic geometry and algebra sort of all piled in one place for this. Now this, remember, when we go back here, this angle right here, okay, that's the phase lag. Or this angle right here is perpendicular to that off of the horizontal axis, that's the phase lag, rho, okay? And that phase lag grows as it grows by you changing the del, the del value here, while keeping the gamma constant. You follow this curve right here now if you keep the friction coefficient, which was 2 gamma, but it's 1 over gamma right here. And you reach the peak right there. That's the best you can do with a high quality, super high quality classical oscillator, or this is the kind of thing you use when you're actually talking about quantum resonance. And it's not an approximation then. It is an approximation for our classical stuff. Okay, we're getting sort of toward the end here. Let's see if there's anything else I need to show about this. There's the dipole with it. You can see that if you take a cross section for that, I don't go to infinity because that's only that point right there. So I make that up and down a real part, and then the imaginary part is cutting across the other way. Here's a way you can solve the thing with a ruler and compass. I really like going back in the history of mathematics, and this is quite a gal. Maria Gaetana Agnesi. And the curve that we've been talking about here, the Lorentzian, it should be called something Agnesi. Well, it is. If you take an old calculus book and open it up where you have a whole bunch of curves in the back, this is called the witch of Agnesi. Now, where did they get that? Well, witches had apparently pointed hats. They aren't as pointed as they are for Halloween this year. They make a cone, right? But actual witch apparently wore a hat with a curve at the top. Okay? So whenever a mathematician talks about a witch, they're talking about some curve that goes up and down. A Gaussian is included in that set, but it really dies off fast, right? E to the minus x squared. But this guy, this is just an algebraic curve. Y equal a constant over x squared plus a constant. Okay, and that's our gamma right there. All right, and this is our del, our frequency difference right there. Okay, for our quantum resonance. Okay, so this is a way that you can draw the thing. All you need is to draw the circle, and then put a bar here, and make sure that every point on the curve hits where that intersects. It's very similar to when we drew the elliptical orbits and we played off of the A line and the B line, right? You just do the same thing here, except now that you're working with a circle this way. It goes this way. So you can make this witch of Agnesi shows, this is out of the, she first of all lived to a ripe old age, but her field was, she did some really beautiful mathematics in the 1700s. Okay, she died at the turn of the century to 1800. She didn't quite make it by 1 year. But, you know, really incredible women mathematicians that don't get much credit for things that are really important. So we are working with the Witch of Agnesi. And she probably, but I don't see any evidence quite yet, that she got the geometry associated with our refractory part, the part that goes like that. I've kind of turned it over here, flipped it, right? Usually if you're going out on the positive axis, you come this way and then go that way. But it's symmetric, unlike the classical green Lorentz function, which is not symmetric. Okay, so those are some things I think that help, you know, this is a whole bunch of constructions actually making both of these curves the same way. You use the circle over here, and then you use the circle up here to make the witch, and you make the derivative of the witch basically right here. And might as well mention what this looks like when you start to get the detuning and the gamma nearly equal. If you get the frequency of the oscillator and the gamma equal, that's called the boundary between damped, just slightly damped. This is critically damped when you make them equal, and then over damped when you make the gamma so big that it's bigger than the natural frequency. And we're not going to talk that much about that, but this is what the Green's functions look like. Now, it's no longer occurring right at the halfway point. This thing never gets to be a peak. It just kind of comes out there and then droops. If I make them exactly equal, the thing just drops off. You can play with that on the graphics. And the flat tire, look at that. Flat tire's huge. The DC response is as big as, practically as big as anything you're going to get as you go to higher frequencies. So this is something that doesn't want to resonate. And it's getting worse if I make the gamma even bigger. Make this circle bigger here, it starts to hang out on the top there. So instead of looking like a circle, it looks like a snail. Right? So this great big flat tire here that represents the DC response. Okay. All right, that's the basic resonance of an oscillator in one dimension at work. That's all. What we have to do next is put two of these together 3 of these together, that's where you're starting to talk about the effect of symmetry and how group theory can let you get solutions without having to solve big matrices. But I definitely want to spend time on 2 oscillators, because that's the beginning of the 2-level system, quantum mechanics, and they are the same equation. So you need to know that. Whether it's classical or quantum, they're the same. But no friction. Well, let that be something for a more advanced class. A chaotic system or something like that. Okay, so that's pretty much it for this part of what I say is most important. Certainly, we can make the case that this is the single most important effect all of physics. Deep down, resonance. So everything's doing. Okay, we'll see you on Wednesday.